So the third problem here is a little bit different than A and B. It's not over chapter 10, the tests, convergence test. It's actually material we've covered since the test. I sent you an email telling you this was going to be featured on this makeup quiz. In fact, I said that the Maclaurin series for either e to the x or sine x or cosine x, you should expect one of those. And so here it is, e to the x. And I'd say about a third of you knew what was going on here and gave me a good answer. Not 100% of them right, but showed me you knew what was going on. And the other 2/3 were confused. So take a close look. Here we're being asked to find the sum. So the way it's worded, these series converge. That's not at issue. And what we want to do is find the sum. And how do I want you to do it? I want you to use the Maclaurin series for e to the x. So of all the materials in certainly chapter 11, the Maclaurin series for e to the x is the most important part. And that is, you'll see it in references to it in other classes. It's just a fundamental result. And so let me remind you, we did this work earlier, and here it is. E to the x, the Maclaurin series, is the summation k equals 0 to infinity, x to the power k divided by k factorial. And just to be clear, let's write out some terms. When k equals 0, that's all 1. When k equals 1, we get x divided by 1 factorial, but that's 1. And then we get k equals 2, x squared. In fact, let's write the factorials here just for the fun of it, even though they don't really do anything until this guy, where 3 factorial becomes 6. And the really wonderful thing about this, it converges. That is, this is true. This series equals e to the x for all x. Powerful word there. And I'll use some exclamation points that are not factorials for emphasis. I mean, it's truly amazing. This series converges for all x. It does not matter. Positive, negative, rational, irrational, it doesn't matter. It converges. And what does it converge to? E to the x for all x. I proved this in one of our earlier videos. If you wanted to know why is it true, you just apply the ratio test to this series. Sorry, this is a power series. Use the ratio test and you'll get 0. So it converges. So that's, your answer does not depend on x like problem 2 on this makeup quiz did. You just get 0, which is less than 1 for all values of x. All right, so part A is intended to be super easy. If you look at the series here, compared to this, you can see that they're exactly the same, except 2 replaces x, and therefore it converges to e squared. Just like that. Same thing on part B. X is ln 5, and so it converges to e to the ln 5, otherwise known as 5. So there's our answer to part B. Now C is just a tiny little bit tricky. I warned you, look carefully at the index. Let me do some erasing here. Maybe that's enough. So notice the series starts at 2. Otherwise, it's exactly the same as the one in A. So this series, part C, is going to converge to the same thing that A did, that is e squared, except it's missing the first 2 terms. Okay, and I warned you, look closely. And so our answer is e squared, but then that includes the first 2 terms. We don't want them. Well, the first term is just 1. And the second term, here it is right here. If you plug in 2, you get 2. So we need to take those guys away. And so part C converges to e squared minus 3. There's our answer. Beautiful. So all of those who took the makeup quiz, I've graded them, posted the scores on Foxtel on the ABC, the combined side. And your grade should be fairly up to date there. I haven't updated the Pearson scores recently. I'll do that soon, although that has a very minor impact on your grade. So I want to go over the quiz rather than give a static copy like I did for the test and post it. I'm going to work the problems here, recording this while I go, and then I can talk about it and explain what's going on. So the first problem here, we want to determine the behavior of these series. So 1 over k squared log k. I think we should have enough experience by now to know that like the ratio test is going to fail, the root test is really unthinkable. I think comparison tests are the only way to go, and we can actually make either one of them work, the regular comparison or the limit comparison. I'm going to work both of them here, just so you can see the details. And of course, then you can decide which one makes the most sense for you. And I suppose it's reasonable to think that problems like these could show up on the final exam next week. And let me also say I'm doing this work on an iPad for the very first time. And no one ever told me I had the neatest handwriting around, and it'd be a little bit worse on the iPad. The good news there is I have a really easy eraser. And so hopefully this will be something you can get some information out of. So the comparison test. Yep, all ready. So for the ordinary comparison test, we need to establish a relationship, an inequality. And I'm going to compare it to the p-series, 1 over k squared, which we know converges because p is 2 bigger than 1. And so what I'm going to prove is that the terms of this series, 1 over k squared, L and k, are smaller term by term than the terms of this series. And if that's the case, then since these add up to a finite number, those will also add up to a finite number. And the amount of detail I expect here, I'm pretty easy to please, but if we're going to put a little detail in, it might go like this. 1 is less than the log of k, provided k is bigger than 3, bigger than or equal. And of course, k is going to infinity, so that's going to be true. Now, multiplied by k squared. Of course, everything here is positive. And now reciprocate. When you reciprocate positive numbers from an inequality, the order changes. And so k squared L and k is going to be the smaller thing now. And 1 over k squared, and of course everything is positive. And that does it. We know the terms of this series 1 over k squared converges. Let's put a little like less than infinity here. This one converges, we know, like I said. And these guys are term by term smaller. So summation 1 over k squared, L and k converges as well. Exclamation point. Okay, that's the comparison test. Pause if you need to look it over. I'm going to go. I said we could do either test, so I'm going to do the limit comparison now. So get rid of that. Oops, grab my pen. And again, I'm going to compare to the p-series 1 over k squared. For the limit comparison, we calculate a limit. The thing we don't know, the sequence, goes in the top. The thing we do know goes in the bottom. Notice those k squareds cancel out, and we get the limit as k goes to infinity, 1 over ln k, which is 0. The log goes to infinity, so 1 over log k goes to 0. Now, 0 is not like the best we could hope for from the limit comparison test. What we'd really like is a positive finite number, and then we would know the series behave the same. But there is, a second and third option to the limit comparison test if you get 0 or infinity for your limit. And so let's take a look at the fact that we got 0. If you go and look at the limit comparison test, it says if the limit you calculate, we just did, if you get 0 and the series you chose converges, it does, then this series converges as well. If the series we chose diverged, the test would be inconclusive. So by, I think it's the second part of the limit comparison, I won't identify the part, and then I won't say something not quite true. It converges. So we had to get a little bit lucky. And, it's not unusual when the log is involved that we might run into those extra parts of the limit comparison. They're good to know. Okay, those are the 2 ways to do this problem, and hopefully one of those made really good sense to you. We'll go on to the next problem. So let me wipe out this. Boom. All right, for the second series here on number 1, part B, there is one test that should just be screaming out at us. If we do just a tiny little bit of algebra, we can write that as k over 3k plus 2 to the power k. And so the root test, absolutely the one to use. You can do it in your head, but I'll write out the details. We're going to take the limit as k goes to infinity, the kth root of something to the kth power. You can see those k's are going to cancel. Then we get just k over 3k plus 2, a polynomial divided by another polynomial. They have the same degree, so their leading coefficients are the limit, form the limit, 1 on top, 3 on the bottom. That's 1/3, 1/3. This is the root test. So how do we conclude? Well, 1/3 is less than 1. It converges. So nice and simple. There is no other test that even remotely seems reasonable. I tried to make it work for the ratio test, and I think it's possible, but I gave up because it was just getting too weird. All right, so there you go. Problem number 1 completed. So we'll put a pause on here and we'll go to the next. All right, here we want to find the radius and interval of convergence of this power series. So I think we want to use the ratio test. I know we want to use the ratio test. Could maybe make the root test work, but there would be one limit, one part of it that we never really figured out. So we could, but we're going to do the ratio test. So we want to take the limit, grab my pen, as k goes to infinity. The k plus first, of course, this we do the ratio test for absolute convergence. So absolute x to the k plus 1 divided by 3 to the k plus 1 times k plus 1 squared. And the ratio test says we divide that. I think we're in the habit. I see you doing this, inverting and multiply. So 3 to the k times k squared divided by the absolute value of x to the k. So some really nice thing happens here. This 3 to the k cancels all of these out, but leaves that 1. Same thing with the absolute x's. All of these cancel all of those and leaves me exactly 1. We can bring those things left over through the limit. There are no k's involved. This absolute value of x and this power of 3 remains. And then we have the limit as k goes to infinity of k squared divided by k plus 1 squared. So that's a second degree polynomial divided by the second degree. The limit is the ratio of the leading coefficients. Both of them are 1, so the limit is 1. And we get the absolute value of x divided by 3 because this is the ratio test. We need that to be less than 1. And it is for some values of x and not for others. So we need the absolute value of x to be less than 3, and therefore the radius is 3. It converges for all x's between -3 and 3. Problem also asks for the interval, and so we know it converges at every number inside. We need to check the endpoints. So if x equals 3, just plug it in to the formula up here. And notice those 3 to the k's cancel out, and we get the p-series. And that converges. P equals 2 is bigger than 1 at -3. If I plug -3 in up here for x, -3 to the k divided by 3 to the k is -1 to the k. So we get -1 to the k over k squared. That's an alternating p-series. And it converges, since the regular p-series converges the alternating one. And therefore, our interval, we're going to add both endpoints. And there we go. The radius is 3. The interval is every number greater than or equal to -3, less than or equal to 3. And that's problem number 2.